Swayam Prabha. Digital India. Educated India.
Welcome to module 9, lecture 6, the last lecture of this module and also the last lecture of the series, concrete technology series. And we shall be discussing about some more special concretes in this lecture and also talk about sustainability. Polymer concrete composite is the first one that we will look into. Then we will look into high volume fly ash concrete, geopolymer concrete, heavy and lightweight concrete and other concretes, sustainability. That is what we will look into. So, this is a sequence of things that we are going to look at. So, you see in 1960s when the 50s 60s polymer development in polymer science and technology took place, and in the meantime concrete science and technologists were trying to enhance the strength of concrete. Now, the strength of concrete is restricted by the is finally the water cement ratio that we have understood, that it is the water cement ratio which governs the strength, and therefore, there is a inherent porosity, capillary porosity in the concrete system, and therefore, its strength could not have gone beyond 40 those days. So, the other alternative was remove the hydraulic cement altogether. Polymer science and technology had developed by that time. Therefore, why not remove the cement, hydraulic cement binder altogether. This gives rise to polymer cement concrete composites, actually polymer concrete composites. Out of this there are three of them. One we call as polymer cement concrete, polymer cement concrete, polymer cement concrete. Then there is another one we call it polymer concrete. A third is a polymer impregnated concrete. So, this is polymer cement concrete, polymer concrete and polymer impregnated concrete. Impregnated concrete, polymer impregnated concrete. Now, is it in this one polymer cement concrete means the attempt is to remove the hydraulic binder. So, here this is actually we do not remove the full thing. In fact, we add some component as an admixture almost 5%, 6% and then use together with the. So, part of the cement system, in the part of the cement system we use the polymeric material, and PC is one where actually hydraulic binder is completely removed, and polymer impregnated concrete is already an existing concrete where we impregnate with polymer. So, this is what it is, polymer concrete composites. First one is the polymer cement concrete. We just had about 5-6%. Hydraulic cement binder with water can be replaced partly by polymers to form polymer modified concrete, mortar concrete for repair purpose, latex modified concrete. Rubber latexes are what are used here mostly, and this rubber latexes, they are actually elastomers. Now, I am sure most of you are familiar with what is a polymer. A polymer is a material which is actually produced from monomers, repetition of the monomers. So, there are varieties of polymers like thermoplastics, thermosets, elastomers, right, the classes of materials. So, thermoplastics are the one which can be remolded after heating, thermosets are one which cannot be remolded, they are usually cross linked polymer system, I do not have time to go into the details of this ones, that could be form of some other course, materials course that you might have done. Now, the elastomers is another class of material which is like which can be, there can be thermoplastic elastomers, but these materials are another kind of polymers which are rubber like, as we understand they have elastic recovery under low strain. So, elastomers are polymers which are elastic, exhibits recovery under low strains. So, latexes are actually elastomers, these ultra fine emulsions after coagulation, and the material behaves like rubber. So, these are small particles 1 to 5 micron, I suppose these are the kind of sizes, very small size rubber latex, spherical particle, spherical particle. Actually, this is added to the cement concrete system, and they behave like rubber, and they get polymerized, solidified, polymerized. So, when polymerization occurs, the mass increases, molecular mass increases, and therefore, it solidifies, and when it solidifies within the concrete system, cement based cement system, 1 to 5 micron means they will go in the interstices of the cement themselves, and thereby they actually increase the strength of the. So, they act as filler, then solidify, reduce down porosity somewhat, and therefore, they increase the strength. So, strength enhancement could be 1.5 times, strength enhancement ratio as it is called, the strength of same water cement ratio concrete. So, strength of the polymer modified concrete divided by strength of the same water cement ratio ordinary concrete non modified could be about 1.5, 1.6 times. So, good concrete can be prepared with this, but this is costly. So, therefore, remained as a repair material. One can make them into flowable micro concrete, been used extensively for repair work. Processing similar to ordinary concrete, only one point, because if you are trying to, you see they come as pre-pack materials, they usually come as pre-pack system, manufacturers supply them as pre-pack system. So, they give you pre-pack kind of mortar for example. So, everything is mixed, you mix water and the material is made, all the construction chemical companies who supply them, they give you pre-pack. But if you are making yourself, then when you are doing this processing almost similar, you must have some kind of anti-foaming agent, because this fine particles, very fine spherical particles, they tend to generate a lot of foams. So, you must have anti-foaming agent. Some plasticizers and other admixtures could be there, but anti-foaming agent is very much required. So, one can actually use this rubber latexes, prepare their own concrete also, but then commercially pre-packed materials are available and very useful in repair works, because they can be free flowing, they can be flowable. So, before self compacting concrete came, this was very much flowable material, and even after self compacting concrete has come, this is used as an extensively as a repair material. Something like this. So, this is your material, you can see the cement and the latex. So, they go inside the system and actually polymerizes. So, once they polymerize, they will actually get inside, and the cement hydrates, cement will also hydration of cement. So, cement hydrates will be there, this will also polymerize, solidify, and therefore, the bond they make it a better concrete as such. So, this is your polymer cement concrete, this is polymer cement concrete. You have all kind of latexes such as basically SBR, styrene butadiene rubber, SBR, styrene butadiene rubber. It is not easy for concrete technologists and cement civil engineers to remember this polymeric name. So, but styrene butadiene rubber is SBR system, is very popular. SBR is very popular. You can have epoxy latexes, polyvinyl acetate PVA latexes, you can have acrylic latexes, etc., etc. There are various kind of system, but this is very, very popular. Butadiene is a rubber, styrene butadiene rubber system. So, this is basically a kind of latexes which are used, and they make the polymer concrete. So, this is one type. The next type is polymer concrete, polymer impregnated concrete. So, polymers impregnated concrete, you have got hydraulic cement binder, and this is impregnated with low viscosity monomer, that is polymerized to form polymer impregnated concrete. Let me see if I have a diagram, I will come back to this later on. I will come back to this later on. Just let us look at this. So, this is your ordinary concrete, this is your existing concrete, and you have pores. These are the pores, as I have shown the blank white spaces, these are the pores. So, these are your pores. Originally they are the pores, actually they are the pores, they are the pores, actually pores are available. So, what you do, you actually, impregnation means put the material, your monomer, with accelerator, etc., because polymerization would be through an accelerator or by radiation technique or by thermal technique. So, what you do, you actually put some heating system. So, you just impregnation, injection is under pressure, impregnation is just putting it on top, flooding it, and then the impregnation will occur, the polymer will get inside, polymer will simply get inside and block the pores at the top, and this is polymer impregnation concrete. So, polymer impregnation can be done from the top on a flat surface, and obviously, the bottom pores are still remaining, but the top pores are there. So, this is the process of polymer impregnation. So, originally you must have a good concrete, low viscosity monomer, that is actually pre-impregnated into the concrete and then polymerized to form polymer impregnated concrete. Now, this polymerization can occur because of the radiation, but that is a health hazard. By thermal techniques, thermal polymerization, radiation polymerization, or by using chemical polymerization with kind of a hardener system, like if you are familiar with possibly araldite, which is of course an epoxy. There are various kind of glues, 2 component glues, or epoxy is one material which is very popular. Now, you have 2 component or 3 component. So, there is a resin, there is a hardener, and maybe an accelerator. So, one of them would be a catalyst or another material which will finally make it to polymerize, right, and there is acceleration, accelerate this process. So, you can have monomer mixed up with those materials all together which will polymerize it, and they get inside and then polymerizes it. So, successfully used in bridge deck, actually the concrete surface becomes impervious, stronger, durable, and high abrasion resistance. The durability is very good. Strength improvement ratio can be as good as 2 in this kind of material when tested in laboratory cylinders, right, and successfully used in bridge deck wearing coat, because wearing coat, what happens is they actually tend to get actually damaged and distressed during, because of abrasion of the wheels and so on. So, what you got to do, after some years you have to put another wearing coat. Now, if you go on putting in that manner, the thickness would go on increasing and dead load will increase. Also, the people, what they thought, they initially thought that they will replace the wearing coat for a given, after a given number of years, not replace, put another layer over a number of years. Replacing is very difficult, but it so happened the traffic increased significantly, the automobile technology improved, more automobile, cheaper automobile market actually increased, and therefore, traffic increased in the system, and when the traffic increased, the wearing coat actually gave off much earlier. Therefore, you have to put in another wearing coat, so repetition, the frequency of putting in wearing coat increased. So, what do? You can't put on, go on putting weights after weights on top of it. Polymer impregnation actually did a very good job there, because once you put that, your wearing coat lasts much longer, its abrasion resistance increased, durability increased, and therefore, it will also protect the inside structural element longer. So, this was polymer impregnated concrete, methyl methacrylate, epoxy, many of those polymers they have been used for this purpose. So, that is what we showed earlier. Well, polymer concrete is simply you replace hydraulic binder completely with polymeric material. So, epoxy concrete also used for repair material, epoxy concrete used for repair material, epoxy concrete used for repair material. So, you have a glue, like for epoxy concrete, for example, GY 250 or 230, these are the brands earlier available. Hardener, glue and hardener HY 830, 850, etc., series, and there is a third component, another. So, you will have this one, you mix the monomer or resin with the hardener system and put sand into it. Now, just simple example, you can take example of araldite. You take example of araldite. It has got a glue and a hardener. Now, you put some sand together in this araldite, it makes you an epoxy mortar. But only thing is, the difficulty is that the mixing process, the viscosity of the system, stickiness of the system is such that it is not easy to make them. So, you have to have special kind of ones. At the same time, you may have to have a spray. For example, might have a silicon spray as a demolding agent. So, normally one would not be using them for regular concrete, because it is so costly. It is you can understand, a small araldite tube costs you how much. Even today in Indian scenario, even if the cement price is high, 50 kilo would cost, let us say 50 kilo costs even 500 rupees, it is only 10, but today it is not 500 as yet, it is 10 rupees a kilo. But epoxy will cost you, araldite small tube cost you, few grams cost you 110 rupees or 20 rupees, 25 rupees, 10 grams. The cost is astronomical compared to concrete. So, this kind of concrete cannot replace our conventional concrete, but can actually do very well as far as repair is concerned. So, quick repair, it will set within 24 hours. So, if you have a pre-stressing let us say a pre-stressing anchor has just gave in, and your system is all locked up, unless you do the pre-stressing. In bridge it can happen, or similar kind of elements it can happen, that if you do not do the pre-stressing, you cannot remove the support system. So, everything gets locked up, and in such situation you want to quickly get the concrete repaired. Epoxy can be a solution there, because it will develop the strength within 24 hours. Curing time is relatively less, but extremely costly. Of course, you have jet cement today. Jet cement I mentioned earlier, they can do the they can quickly set and all that. So, airport runway repairs, particularly during the war time, could be such jet cement. Epoxy is costly, so it is not used, but epoxy have similar kind of properties. Quickly epoxy concrete. You can have polyester concrete, PMMA, polymethyl methacrylate concrete. All these concretes have been used. The strengths are much higher, because the inherent capillary porosity business is not there, but cost being higher, not used for conventional structural element, only used for repair work, So, these are your polymer cement concrete, these are our polymer cement concrete system. Let us look at a new concrete called heavy concrete, used for radiation shield. The major problem in a nuclear reactor is to attenuate the gamma rays and neutrons emerging from the core by means of biological shield. This should provide a kind of shield for biological shield. So, you do not want gamma rays and neutrons must be going out. This is overcome. You have the cheapest way and most convenient material chosen is a heavy concrete. And what do you do in this one? You have heavy aggregate, hematite aggregate, barite aggregate, the aggregates which are very strong. So, this is called heavy concrete. Quick introduction to this material. Essentially, you have X-ray photons, photon energy, etc., etc. The after attenuation, this is your thickness. Basically this should be your concrete. So, when it passes through the material, some object, which has got a thickness, a density, and this atomic number, actually it will attenuate, and if this radiation is allowable, this is fine. So, heavy concrete is based on this principle. I, the radiation that you get is I0, that is incident radiation, and e to the power minus mu x. So, this mu depends upon density, thickness, etc., etc. X is the thickness, mu depends upon, amongst other things, it depends upon density. There are a few other factors. So, therefore, heavy aggregate we use barite or hematite, and their specific gravity says 4 to 5. So, this is the concrete. Obviously, here the mixed proportioning is not quite different from the conventional concrete. Finally, it will be the water cement ratio, and all other properties of the aggregate, whichever governs the strength of concrete, it will be the same. So, heavy concretes are used for radiation shield. Lightweight concrete, on the other hand, we use for insulation purpose. Now, you remember thermal conductivity. Thermal conductivity mainly depends on aggregate type and of course, the porosity of the aggregate and nature of pores and obviously moisture content affected, right. Now, this means that the density, it will depend upon density. So, thermal conductivity has become more important than ever before, because of what you call energy efficient building design and so on so forth, operational energy consumption in conditioned building. So, thermal conductivity is very important, insulation, thermal insulation is very important from that point of view, and the concrete thermal concrete that can provide these are actually lightweight concrete. So, lightweight concrete. How lightweight? Well, essentially because low porosity, high porosity means lightweight. So, thermal conductivity depends on aggregate type of course and the porosity. Aggregate is the one which conducts, which has got the conductivity of its own, but the porosity is one which governs it, and obviously nature of the pores also governs somewhat, but I think I am not interested in telling you about what is the kind of nature of the pores and so on and so forth. So, it depends upon conductivity of the solid and pores, and the solid conductivity will depend upon mineralogical composition of the aggregate. For example, quartz or quartzite has got very high thermal conductivity compared to other type of aggregate, So, lightweight concrete will depend upon is basically because of the porosity. Low porosity, high means high density, high porosity means low density. Now, lightweight aggregates were the other kind of aggregates which is generally not available much in India. You have something called cinder concrete, not a structural concrete, but cinder or overburnt bricks, they will give you lower density, would give you somewhat good thermal conductivity. But in India, it is aerated concrete, autoclaved aerated concrete or foam concrete, these are the ones which are used as lightweight concrete. So, you have got aerated concrete actually, autoclaved blocks, foam concrete. Now, this the foaming agent, you have some sort of foaming agent, aluminum powder, or there is even organic foaming agents these days. So, you make foam and put it into the concrete or mortar that you make, and you can make foam concrete. There are some agents which you can add in the concrete right in the beginning. They will go into the concrete system and generate a lot of foam or void system gases, and this entrapped gases can give you aerated concrete. Now, this curing of this one can do autoclaved. So, using fly ash, sand, one can use even river sand on those ones, fly ash, sand and part cement, one can actually then use autoclaving at high temperature, blocks can be generated, and that gives you fly ash or various kind of blocks and the concrete there. There are even in formwork also you can produce actually with a foaming agent, autoclaved, aerated concrete. So, these are used for particularly used for thermal and acoustic insulation, particularly for thermal insulation. Also, they serve as lightweight. So, they can serve of course, by the porosity at the front, they can reduce down the provide you some kind of sound insulation. Sound insulation actually is function of the mass of the wall, larger mass more insulation, but absorption property is the function of the surface. So, where if you have porous surface, that absorbs more. So, lightweight aggregate concrete also, if it is used as a core in a sandwich panel, you have two, this is one, this is another panel, and you have a third sandwich material here. So, that is a sandwich one. So, this is the one, this material will take this load let us say, and inside material can be lightweight material which will act as thermal insulation. Whole system can give you good acoustic insulation also, because layered system gives you good acoustic insulation as well. So, these materials are used for such functional purpose, and lightweight aggregates are of course not much popular in India, because they are not available. Natural lightweight aggregates are available elsewhere in the world, but you can have lightweight aggregate generated from fly ash by sintering process. So, you can have synthetic lightweight aggregate coming from sintering process, and aerated concrete I have already mentioned. A variety of another concrete is no fines concrete, which is pervious concrete, but I will come to this. Just before, let us see, the thermal conductivity is a function of porosity in dry state, and it is also a function of porosity in saturated. So, saturated case, this is saturated, this is dry, this is the thermal conductivity. So, as the porosity increases, thermal conductivity reduces significantly, porosity increases. Now, here is your 888 concrete somewhere, very small, 0.02 watt meter degree centigrade. Even in saturated condition, they will be 0.4 or 0.5, while normal aggregates are here. This is for concrete actually. This is normal aggregate would be somewhere there 2.5, and at saturated condition 4, etc., with quartzite aggregate. Other aggregates might show you somewhere there. So, you see, you can generate actually lightweight concrete here, but even normal concrete, their thermal conductivities are of these varieties, orders are known to us. Saturated condition with moisture, they give you higher conductivities. The pervious concrete allows water to percolate through it, no fines. Now, you can actually have only the, you have to also find out the strength is sufficient. So, no fines, there will be voids in the system and interconnected voids in the system. For water harvesting, they could be a useful thing. The pervious concrete could be useful for water harvesting, but they can serve also as good insulation. They can also serve as good insulation, provided you are able to make them and put them in the right kind of place, where you do not want moisture to percolate, because if you put it on the rooftop, the water percolates, then is going to be no use, but they can also, depending upon the situation. So, no fines concrete, you leave voids. Basically, you have system like this, aggregate system, and paste will go. Do not put in sufficient paste to fill in all of them, or even if you put the, it has to be controlled, otherwise the cost would be high. So, one is to see that. People are also trying with kind of polymeric balls or polymeric hollow aggregate system, plastic aggregates and so on. There are several other attempts are being made to get actually lightweight concrete, and these are all at those stage. But aerated concretes are reality, and lightweight aggregate concrete elsewhere in the world are also reality. Their strength actually reduces down, you can't get very high strength concrete with them, because aggregate becomes a weak point. So, this is about lightweight concrete, heavyweight concrete to lightweight concrete. Recycled aggregate concrete using waste in concrete of varieties kind. For example, people are trying all kinds of waste that is available for other industries to use, because sand is a problem, availability of the fine sand as fine aggregate is a problem. On the other hand, you have got huge quantity of pond ash, bottom ash as fine aggregate. This you can use as fine aggregate. There is a huge quantity of pond ash available, bottom ash available as fine aggregate. All right, pond ash available, bottom ash available as, and that you can use as fine aggregate. But one must design the mix, characterize this material and design this mix. One must characterize this material and design this mix. Some, it's one can use them successfully, there is no problem. Bottom ash got another advantage. If you are collecting directly from the thermal power plant, they can actually give you good thermal insulation as well. However, this materials are to be seen and designed, because there are component of spherical particle there and hollow phase spherical particle, and generally they have low density is lower, but strength can be higher. So, therefore, pond ash as bottom ash as fine aggregate. This pond ash is nothing but the ash, bottom ash and fly ash mixed together, they are ponded for disposal purpose. Where variation, they vary from point to point in the ash pond, but they can still be, the sizes are similar to fine sand, and therefore, one can use them. Recycled aggregate, demolition waste, construction waste, they have to be crushed and make into a aggregate. These are in research stage, still have to be used, but these are possibilities. People are attempting them. One problem associated with this one is, whenever you take the aggregate, recycled aggregate, crush them, you will have an original mortar layer adhering to it. The interface, original interface remains. So, when you add now your mortar, new mortar, fresh mortar, they would again form an interfacial transition zone. So, original interface remains, and people are trying to solve them. Now, you have to increase the strength. So, therefore, one has to see limitation of the strength should be there. Good lot of research are going on to look into this material, grade them, first crush them, get them graded, get the packing density and obtain the system as it should be. So, this is the recycled aggregate, there are a lot of research being done on this right now. Another concrete is high volume fly ash concrete. Percentage of fly ash can be as high as 50 to 60% in this one of the cementitious material. So, you have 100 kg of cement or maybe you just have 100 kg of cement developed largely in North America, Canada and United States. 100 kg of cement, maybe you will have 100 kg of fly ash or maybe more 120 kg of fly ash. So, this is the material you use. Now, whole idea is to use whole idea where you do not want where you do not want too much of strength wanted is not very large, where you do not want large strength, but you want to use a lot of fly ash, then this material is there. After all, fly ash is a waste and you are saving onto the cement. We will come to that in short while. And in such situation you can use this material very well. But how do you use this? To get structural grade of concrete 20, 30 MPa, 40 MPa concrete. Use superplasticizer to cut down onto your water. Use superplasticizer to cut down onto your water and use low water cement ratio, low water to cementitious ratio, low water to cementitious ratio. So, therefore, initial strength will be given by the cement. So, 0.32 for 60% fly ash, 0.45 for 50% fly ash. So, use low water to cement ratio, use a superplasticizer to get the workability. In fact, fly ash can improve your fly ash actually because of its spherical shape, as we have seen earlier, it actually acts like a somewhat like a water reducing agent. It cut down so to your water demand. So, therefore, both fly ash and when these are used judiciously, normally we use low water cement ratio for high strength in normal concrete, but here I am using low water cement ratio superplasticized, but using large quantity of fly ash. So, my strength may not go high, but it will be normal strength concrete, but large quantity of fly ash I will be able to utilize. Low RD strength, because I am using fly ash, low RD strength, and then good long term strength and durability I will obtain. Well, the question of reinforcement, if it is there, then the issue of carbonation, these are to be looked into. So, high volume fly ash concrete has been a development, largely it will give us it can make it to be a sustainable concrete, because cement saving would be there. Then there is another concrete of the similar kind called geopolymer concrete. Now, this does not use cement at all, that was high volume fly ash, but no cement, high fly ash, less cement, but now no cement, fully fly ash. Basically, it is carbon and silicon belong to the same group in periodic table. Therefore, this silicon also shows polymerization tendency. It can form bond with silicon to silicon, SiO, Si bond possible, 4 valencies. So, this also it can show that similar properties as carbon. So, it can be polymerized limited extent. So, this is reaction of aluminosilicon silicates with alkali polysilicates, utilizes polycondensation of silica and alumina and high alkali content for strength. So, basically condensation reaction is a polymerization reaction, where all the product they actually react leaving no byproduct to make a polymer. So, polycondensation reaction is that. So, everything goes into it in high alkali, and then this is because of polymer solidifies and therefore, it gives you strength. So, basically initially plastic, then polymerizes, becomes solid, and it can give you the strength. One problem has been curing temperature is 60 degrees centigrade or so far as understood, and therefore, but remember it does not use any cement altogether. A typical mixture of this geopolymer concrete would look like this: 20 mm aggregate, about 277 kg per meter cube of concrete, coarse aggregate 40 mm, this is the second coarse aggregate 370 kg, and 7 mm 647 kg. So, you have actually 277, 370 it will depend upon packing density. 647 would make it something like 1200, you know. So, 14 9 1294 kg of quartz aggregate, 1294 kgs of quartz aggregate. Fine aggregate is 554, it is a fine sand. Then use fly ash, low calcium, because this is the binder now. So, this is 480 kg, 408 kg per meter cube, this is the binder, together with sodium silicate and sodium hydroxide, you know, 103 kg, this is 41 kg. So, silicon to sodium oxide ratio should be equals to 2. Actually, the concentration is pretty high, you know, it is rich. For example, this is 8 m, this was 14 molar concentration, this is 8 m concentration, this is 14 molar concentration. So, high concentration of sodium silicate solution, sodium hydroxide solution. Then use a superplasticizer to actually disperse the system, and you might add extra water 22.5 kg etcetera per meter cube. So, this will have some water in the system itself plus this water. So, what you are using? You are using fly ash, sodium silicate, sodium hydroxide, and of course, rest all is like concrete only, and then you make this concrete 60 degrees centigrade curing temperature is 60 degrees centigrade, you know, 60 degrees centigrade is the curing temperature, that is the only the problem that is there. Curing temperature is 60 degrees centigrade, 60 degrees centigrade curing temperature, and that is, you know, somewhere around that, and that is actually the problem. Besides the problem of purity of this one, you know, this molarity and this molarity, such strong concentrated material, pure material you got to use, and therefore, the cost is actually high. Cost is not yet, it is not, you know. So, more research is required, you require more research in this, but once successful, it may actually do away with the cement, lime based cement altogether. Well, there could be something new coming in, magnesia based cement coming in the meantime, and several other things are actually really being worked on. Now, so far what we looked into all the types of concrete, varieties of concrete, and remember we talked of so many types of concrete right in the beginning in the first lecture. We said normal concrete, high strength concrete, and high strength and high performance concrete, high strength matrices, roller compacted concrete, self compacting concrete, and you know, a whole lot of them we discussed actually. But one issue of concrete we got to look into called sustainability. It should sustain. What is sustainability? To use the resources, currently available resources, in such a manner that it does not affect the use by future generation. So, that is it, use all materials, energy, everything in such a manner that it does not affect. I am not going into a formal definition of sustainability now in this last lecture, but because I have other things to talk about, but this is a whole, you know, set of literature available on this issue, but it is relevant to our concrete very much. And first thing in this issue is of course, the embodied energy. Cement production uses energy, also emits carbon dioxide, because you are calcining calcium carbonate. So, it emits actually carbon dioxide. It uses some amount of energy. So, therefore, that energy which is used in cement production, it is called embodied energy. It will include the transport of raw material. You can go further down below. There are other concepts such as exergy and so on, are so many things. I do not think we are going into this, but embodied energy is the energy that is gone into the materials from production up to the construction in our case. So, the energy used in production and transportation of the material is called embodied energy. So, this is there for cement. Aggregate may require, if you are crushed aggregate, may require some energy for production, mining, and then today in future surely it will be mined only, open cast mines as they are in many of the western countries. Quarry, even if you are taking out from the quarry, you are crushing it, there is some energy going into it, then transportation. So, therefore, similarly fine aggregate, transportation as well as energy required in production, they make the embodied energy. And then OPC produces carbon dioxide, and it is actually next to fossil fuel. in production of carbon dioxide, which is a greenhouse gas, as you know. What is a greenhouse gas? A greenhouse gas is one like carbon dioxide, methane, etc., water vapor. You know what is a greenhouse? For example, if you have a glass house, which you might have seen in hill stations, the glass allows short wave radiation to pass through it. So, it allows sunlight to come through it, but does not allow long wave radiation to pass through it. So, it is transparent to short wave radiation, opaque to long wave radiation. As a result, in a greenhouse, temperature is maintained high if there is sun's radiation available. So, in cold countries it is very important, even in hill station in India, the plant rooms, where you have small plants in nurseries, you have greenhouses, where actually the glass or some transparent material which allows short wave radiation or solar radiation to come in, but opaque to terrestrial radiation, which are long wave radiations. So, carbon dioxide layer formed on top of the atmosphere is almost acting like that, and that is causing solar radiation to come in, but getting trapped. Normally within a year, whatever radiation comes in from the sun, it actually gets dissipated to the atmosphere in some manner or other by radiation back, evaporation, transport, so many mechanisms. We are not going to this, but if the carbon dioxide is there, it does not allow radiation to go back. So, it is trapping, and that is causing global warming. So, this is a concern. So, cement is the next to fossil fuel in terms of this carbon dioxide production, anthropogenic carbon dioxide 5 to 10%, and therefore, it is very important to look into this. And India of course, is the second largest producer of OPC, and it is OPC only, it is the OPC only. So, OPC after China, and therefore, this issue is very important for us. And then if you look at this, the volume of concrete we use, because we have said concrete is a very economical and many other advantages are there. So, because of its volume of concrete use is very large, the cement is the material used by mankind next to water. Water is maximum, then you use cement or concrete. So, per capita concrete consumption in the world is increasing also astronomically, need not go into that details at the moment, but because of sheer volume of cement, concrete is the major contributor to embodied energy in most of the buildings, but it is also a major contributor to carbon dioxide in the atmosphere. So, that is why 5 to 10%. So, hence contributes most to the carbon emission in the initial stages. In its initial stages, it actually contributes maximum to the carbon. So, therefore, concrete and green construction, this is very important. So, it should see that how concrete reduces, and one of the culprit is of course, the OPC clinker production, and that is why this high volume fly ash concrete came by. Geopolymer concrete is being looked into, magnesium based cement is being looked into, and several other issues are being looked into. Now, the major contributor to embodied energy is most building, and as we said, it is next to the OPC cement. Typically, if you see it in buildings, in a given building, because of the quantities that is used, masonry would be embodied energy gigajoules. If I look at it, typically in a building, masonry will be there, steel will be there, although steel per metric ton per metric ton embodied energy produced by steel is much more. Plastics, but concrete being sheer volume, it is actually the largest producer of largest contributor to embodied energy is building. So, one issue is embodied energy, the other is of course, the operational energy, because after in buildings and of course, infrastructure embodied energy itself is good enough, concrete is not going to add to the or save the operational energy in any manner. So, one must look at life cycle energy implications in all cases, life cycle greenhouse gas contribution, that is one should look into as far as concrete sustainability is concerned, and contribution to natural resources depletion other than those used as fossil fuel, because fossil fuel is already taken care of there, right. So, for example, sand, today in India sand you can't get river sand, environmental problem, you have created ponds, pits in the river, changing the river by taking sand from the river, you are actually disturbing the system of the river, ecological and environmental system of the river. So, you can't take sand from there. So, therefore, depletion of the natural resource, this has already occurred, but we should not deplete it more right now so that future generation gets more affected by various manners, by not able to use the resource for themselves, but environmental concerns all put together. So, natural resource depletion is an issue. Similarly, coarse aggregate resources are, they are not increasing, they are decreasing. So, therefore, one has to keep that into mind. So, natural resource depletion is what one should see, and that must be taken in. So, sustainability performance of concrete should take into all these issues, and that is why you have high volume fly ash, geopolymer concrete, magnesium geopolymer concrete and magnesium based cements, and these are being thought about. Minimization of the cement consumption is very, very important, because durability, it should be more durable, maintenance free, durable, maintenance free. If you do more maintenance, lot of cement again you are going to use, where OPC might contribute. If you are using polymer, there also again polymers also, they will contribute to some kind of energy usage and so on. So, this issue has to be looked into, and therefore, sustainability performance, when one talks about concrete, one must look into all these issues put together. And therefore, let me summarize this lectures all together one by one, and I will take a few minutes in this summarization slide. We have looked into concrete. From the last one we looked is that it is sustainable, it can be sustainable. Now, how it can be sustainable? Minimize carbon emission, carbon dioxide emission, that is, reduce the use of OPC clinker as they are produced now. How can you do it? Use of supplementary cementitious material. Surely, use of high range water reducing agent, because particularly supplementary cementitious material like fly ash, which is actually otherwise a problem of storing from environmental concern, they would create environmental disturbances. So, use this material in concrete, even in structural grade of concrete, if you have good structural grade of concrete, if you are not using high volume fly ash concrete. So, they should be used, and so is a plus water reducing agent, because water reducing agent can reduce the use of water, and hence for same water cement ratio you can use less cement. It has got its implication on economy also. Attempt to use recycled aggregate, lower recycled aggregate as much as possible, or recycled material as much as possible. At the moment, coarse aggregate may not be very easy to use, but surely pond ash, bottom ash, and waste from, let us say, marble industry and other industries, if they are characterized properly and researched properly, they can also be used. So, to make concrete sustainable, these are the thing. First is the, and also its thermal properties if you are using in building. So, one must look into, because it can, concrete can store energy, it has got what is called thermal mass, it can store energy. So, these issues are looked into. Then radiation, rejecting the radiation, this depends upon what is called emissivity of the surface, long wave emissivity. So, the color, and of course, now people are using nanotechnology, for example, titanium oxide on concrete might produce, or various kind of admixtures and so on, a concrete which is self cleansing concrete, and several other attempts are being made. So, these are trying to make concrete sustainable. So, this was the last one I looked into in the summarization, but first of all through our 42 hours of discussion, what we have observed? Concrete is versatile. Where does the strength range from? 5 MPa to 200 MPa, maybe 800 MPa cement based composites. So, it is really versatile, very, very versatile material. It can show you, you can design it for strength as you want. Put fiber into it, you can get right kind of ductility that you desire, but if you do not get it, tensile strength improvement is not as much. You can obviously use reinforced concrete or pre-stressed concrete, but tensile strength also can be enhanced perhaps in future. If you look at moldability, roller compacted concrete, zero slump to self compacting concrete, again it is versatile, very high range. The tensile strength and ductility of course remains problem for normal concrete, but then we do not use concrete as such in most of the cases. We use that as a composite, as reinforced concrete, or we pre-stress it the way obviously providing reinforcement. It can provide robustness, massivity. A mass concrete dam, you can make it concrete, or of course, good old days could have been with masonry, but largely concrete provides that answer. You can't use most of the other material. For example, you can't use a plastic polymer to really make a robust gravity dam, but concrete can provide you that. It is economical, it is cheap, and that is why it is used so much. It is relatively durable, more durable than many materials, and you can make it more durable. But many understanding are yet to be developed. Lot of things are still on empirical stage, particularly with reference to this. So, research are required and they are being done. Development as concrete has taken concrete to a new heights in last 1 or 2 decades, last 2 decades of 20th century and following it up. So, therefore, it has actually given you real versatile material is available in terms of concrete, and it can be made sustainable, and there are of course, more kind of attempts are being to make it more and more sustainable. So, therefore, with this we can conclude the concrete is a versatile material and can be used, and in discussions, in our discussion right from the first to the last lecture, we have tried to look into all those aspects of concrete. Thank you very much for bearing.